Hi Nicola and Lisa. Today we're going to start a new topic on complex numbers, and this is a topic which is part of the SAT syllabus. I thought it would be a nice topic for us to work on over the next few weeks. It describes things in relation to the number I, and I is the square root of -1. Now I'll explain a little bit more about that in a second. But I think this is a great topic because it leads on to some really interesting graphical interpretations of mathematics. It starts off being quite algebraic, but ends up being quite graphical. So I'm going to give you a quick tutorial on how to work with these. We're going to add them, we're going to subtract them, we're going to multiply them, we're going to divide them. You get some really interesting fractal pictures from these numbers. So give the worksheet, which I'm going to send to you this morning, a go, and I'll be online if you need some help. Bye. As an introduction, I think we should just first of all talk about different types of numbers. You get natural numbers. Natural numbers are whole numbers, positive numbers, so 1, 2, 3, and so on. Those are natural numbers. After natural numbers, people often start talking about integers. Integers are the ones that include negative numbers too, so you've got like -3, -2, -1, 0, 1, 2, and 3, and they go in both directions. Those are the integers. Then of course you have rational numbers, fractions, decimals. Often they're all grouped together as rational numbers, but if I just jump one step ahead, we can talk about what we normally talk about as numbers of real numbers. We've used that term before. Real numbers are any numbers really. They can be fractions, so they can be 2/3. They can be irrational, so they can be the square root of 2, or they can be pi. They can be whole numbers, of course. They can be negative. They can be all sorts of different things. Real numbers are really all the numbers we generally use in a mathematics lesson on a daily basis. But there's one step ahead of this, and that is the complex numbers. Complex numbers include a special type of number, and that number is I. Complex numbers look like this. So you can have like 3 plus 7i, or you could have 4 minus 6i, and all sorts of different things. You could even have like a negative number at the beginning, -2 plus 2/3 i. And this I is a special thing which I'm going to explain in a second. But a complex number has two parts to it. It has a number at the beginning and it has a number at the end. And the number at the beginning is the real part of the complex number, and the number at the end is the imaginary part of the complex number. And when I say imaginary, it doesn't mean it doesn't exist at all. It's just the term we use for I is the imaginary part. So let's talk a little bit more about what I is. I crops up in lots of different places, but it's defined as being the square root of -1. And that's a definition of I. And people started using complex numbers because they became useful in solving problems, in solving mathematical problems, algebraic problems. They have all sorts of applications in engineering and science. But let's just talk a little bit more about what this is. It really becomes an algebraic expression. We use an I like we would use a variable in an equation. So you can have I plus I, and that makes 2i. There's certain sort of logic that you're already aware of that you can use with complex numbers. If you have 3i plus 7i, that makes 10i. So it works like collecting like terms. But because the square root of -1 is I, we have to do something when we start multiplying together. So if you have I times I squared, that would be the square root of -1 multiplied by the square root of -1. And we say that's equal to -1. You could interpret I squared in different ways. You could say that the square root of -1 times the square root of -1 is actually equal to the square root of -1 times -1, which would be the square root of 1, which you would expect to be 1. But actually we define this specifically as being I squared is equal to the square root of -1 times the square root of -1, which equals -1. Just like if I had the square root of 7 times the square root of 7, the answer for that would be the same as 7. So we have this new type of number which is called I, and it's defined as being the square root of -1. And we have complex numbers which look something like this, where you have an ordinary number at the beginning and then you have an imaginary number at the back. but the coefficient in front of the I here is a real number. So you basically have something which is this sort of style. It's a plus bi, where a and b are real numbers. But this together makes something which is a complex number. And this complex number can be used to solve problems. It can be solutions to equations, can have complex roots. You can have all sorts of different things, and you can work with them just like other numbers. It's like an extension of the sort of numbers we were talking about earlier. With natural numbers, you have simple numbers that can be the simple solution to problems. With integers, you have a bit more flexibility. When you get to real numbers, using irrational numbers, fractions, you can do lots of different things with that. And complex numbers opens up the world of numbers even further. We can solve problems which have complex solutions where previously we might have ignored them. So for example, often you have a problem like this. You could say, well, the square root of 49 is equal to 7. But previously I might have asked you, what's the square root of minus 49? And we would have said, oh, there's no solution to that, we don't know. But actually, this can be broken up into the square root of 49 multiplied by the square root of minus 1. And that gives us 7i. So it opens up a whole new world of different solutions to things that previously we said didn't exist. So it's really stepping outside of the boundaries of normal maths. Let's just do a little bit of arithmetic here. Let's say we have two different complex numbers. Let's have the first one. I'll call this first one Z1. And this is going to be 2 plus 4i. I'll have another one, Z2. Let's say this one is 10 minus 6i. Now we can combine these together in lots of different ways. You can multiply them all the way through by a number, just like it's a very algebraic operation. It works a lot like manipulating algebraic expressions. So I could have something like 10z1. That would just be, that's going to be a 1 there. 10 times z1 would be 10 times all of that, which would give me a new answer. 10 times 2 is 20. 10 times 4i would be 40i. So you get another complex number by multiplying it by 10. I could add these two complex numbers together, z1 plus z2. That would give me 2 plus 4i plus 10 minus 6i. And we collect like terms in the same way you would do with algebra. You can add the two real parts together, so I get 2 plus 10 is 12. And these two are considered like terms as well. We can have 4i take away 6i, which will give me minus 2i. In a similar way, you can subtract things. So I could do, let's say we have 2z1 take away 5z2. So I now need to multiply this one by 2 and this one by 5. So I'll have 4 plus 8i take away, I'm going to put this in brackets just to be careful because of the negative numbers involved. 5 times this one, 5 times 10 is 50. 5 times 6, 5 times minus 6 gives me minus 30i. And then I'm going to subtract all of this away from all of this, but I can basically subtract away the real part. So 4 take away 50 would give me minus 46. And 8i take away minus 30 would be the same as adding 30. So I've got 8i plus 30i, which gives me plus 38i. So the operation I'm doing here, it may be with this new style of numbers, but it follows exactly the same sort of algebraic rules if I was doing something involving a's and b's or x's and y's. So these are complex numbers, and complex numbers open up a whole new world of solutions. And it's quite a nice thing to know the basic properties of these before we step out and do the equations. But you can add them, you can subtract them, you can multiply them, and you can divide them. But I think I'll leave that for another video.